Today we're going to pick up at chapter 6.6, discussing molar mass and chemical compounds. Okay, so first let's describe what is molar mass. As the name implies, it's the mass that's relative to the amount of a material, in this case, a molecule. Okay, so this is really nothing more than what we've encountered when calculating the atomic mass. As a matter of fact, the molecular mass can be obtained by adding the mass of all the atoms within the molecule. So shortly, it's the sum of atomic mass of atoms in a molecule. So this would just require that you keep in mind that you can have moles of different materials. You can have moles of atoms, you can have moles of ions, and you can have moles of molecules. A mole is simply the amount of a substance. And we're familiar that this number comes from Avogadro's experiments, and it's 6.022 times 10 to the 23rd. So it's important to indicate that our unit will be in grams per mole. Therefore, we can see clearly that if you know the molecular mass of a substance, or if you know the moles of a substance, or if you know the molar mass of a substance, you can rearrange this equation to solve for one of the items in the case of something being unknown. Also, the fact that we have a ratio of grams to moles indicates that we can easily use molar mass as a conversion factor between moles of a substance or mass of a substance, depending on which is unknown. In order to provide an example of how to calculate the molar mass of a substance, let's use water. Okay, so we need to first identify our basic equation so we can plug in the things which are unknown. So molar mass itself is equal to the molecular mass. in grams of a compound, and this is divided by the moles. In this case, the compound is water. So let's identify the molar mass. We know that by the definition, molar mass equals grams per mole. So the per indicates we just need 1 mole. So 1 mole of H2O, we have this bottom portion. So if we can calculate the top, if we can identify the molecular mass of water, then we can determine the molar mass of water. So what's the molecular mass of water if you have 1 mole? To solve for this, you need to determine the sum of the atomic masses. So we have 1 hydrogen atom, 2, and 1 oxygen atom. And we're going to add this and again, this equals the sum of atomic masses. So the atomic mass of hydrogen is 1.0079. The atomic mass of oxygen is 15.994. So we'll just compute that. And this comes out to 18.0153 grams. Okay, so this is relatively easy. We just then divide the molecular mass by the moles. And now we have the molar mass of water is 18, essentially 18 grams per mole. So as you can see, there's really nothing difficult in terms of identifying the molar mass of a substance if you know the molecular mass. So this is really becoming an exercise in calculating the molecular mass. So let's examine another molecule. Vanilla. It has the chemical formula C7H8O3. And if we want to determine the molecular mass, just like with water, we're going to get the sum of the atomic masses. Okay, so this is very simple. we have 7 carbons, we have 8 hydrogens, and we have 3 oxygen atoms. Essentially, we just replace the symbols with the corresponding atomic masses. And then we compute. All of this comes out to equal 140.1384 grams. So this is the molecular mass of the molecule vanilla. So in chemical calculations, we can say that this is equal to 1 mole of vanilla. From this equality, we can generate a conversion factor. This is essentially 1, since they're equal, they're just representing different units, so it's convenient for converting from moles of a material to grams, in this case specifically vanilla. So if I were to have 10 to the negative 6 moles of vanilla, and I was curious about how many milligrams this would produce, I would just multiply these two values. Moles would cancel out, my unit would be in grams, and I know that I can convert this into a prefix instead of writing out the long number, which equals about 140 milligrams. So this is a clear example of how to not only determine the molecular mass of a substance, but also how to create a conversion factor from that equality of the amount in grams to the molar amount. And once you have that conversion factor, you can use it to determine the grams of a material once you know the moles of a material. So this is the useful function of determining the molecular mass or the molar mass. So although that's pretty easy, it's still useful to recognize that some of the skill that should be developed in chemistry is not only identifying the names of compounds and their formulas, but also to generate a structure or to go from a structure to a formula. So if you were giving that you have a material with a certain structure, you should be able to determine the chemical formula. Or if you're given the chemical formula, you should be able to predict the structure. So this representation of vanilla is almost complete. However, we could add more detail by showing which materials have non-bonding electrons, additionally, we have to make sure we have the appropriate number of bonds on each of our carbons. This carbon is only bound to 3 other atoms, so we need an extra bond here. This carbon needs to have another bond, so it's going to have an extension with hydrogen, just like these. This carbon needs a second bond, and this carbon needs an additional bond. Okay. So it's important to recognize that once you have a chemical structure, you can produce a chemical formula, and vice versa. So we have come to recognize that there are different types of chemicals, and we've just looked at molecular compounds, water, vanilla, but there's also ionic compounds, and the calculation is the same for the molar mass of ionic compounds. However, the terminology is different. So the ionic compounds have formula units. So you calculate the molar mass of an ionic compound using the formula mass. And this is a ratio of the formula mass of a compound and the moles of the compound. The reason that the ionic compounds use formula units is that they don't share electrons like molecular compounds. So instead of their chemical formulas, for example, in the case of ammonium chloride, represent a formula unit. So we can think of units as like building blocks, the basic or smallest component of a larger size structure. For example, we know that if you have a cube, that if you divide this in a certain number of pieces, depending on the size of the cube, you can attribute certain properties to that unit. For example, we know that 1 liter equals